It is your responsibility to understand and apply all requirements of the Canadian Electrical Code Part 1, including those not addressed in the training. Do you want to know?
Hi, I'm Roy, your subject matter professional for this learning. I will help you to understand and be able to apply the requirements of this section of the Canadian Electrical Code, Part 1.
The aim of this training is to provide new knowledge and to support the development of new skills that you can apply immediately to your job. The purpose is why you are taking this learning. To directly support the purpose, this learning has identified objectives. Here is what you will learn as you take this training. This training is divided into topics. These topics build on each other, so a best practice is to review them in the order they are presented. Save or print a copy of the Quick Reference Guide. It is located in Resources. Use this Quick Reference Guide to take notes and as a practical job aid for this code section.
All electrical circuits and apparatus are subject to accidental overloads, short circuits, and ground faults. These events can be very dangerous, so Rule 14-010 is designed to provide protection against these events. First, it requires that a device that will automatically de-energize the circuit if the current reaches a high enough value to cause thermal damage to the conductor. Additionally, circuits and apparatus have a manually controlled device that will disconnect all the ungrounded and energized conductors at the same time. In situations where a voltage failure or a reduction in failure could cause injury or fires, the code requires a device that will open the circuit when the voltage fails or drops below a safe operating level. The current flowing into a circuit during a fault must never be more than the let-through current, as shown in Figure 14-2. Equipment used to open a fault circuit must have a rated voltage that is at least the let-through rating where it is connected to an electrical circuit. All electrical equipment intended to clear fault currents must have an interrupting rating at the rated system voltage that is not less than the maximum available fault current rating, short circuit or let-through, where it is connected in the electrical circuit. The equipment must be able to open under both full load and fault conditions. Having the proper voltage rating is crucial for the equipment to operate as intended. Also, as seen in the picture, it should be noted that equipment such as breakers with multiple voltage ratings may not have the same interrupting rating for each voltage listed, 18,000 amperes at 480 volts compared to 14,000 amperes at 600 volts. Fuses are capable of interrupting their listed current at any voltage up to the voltage listed. Electrical equipment that interrupts current at other than fault levels must also be rated for the system voltage and the maximum current that the equipment must interrupt. Examples include circuit breakers and fuse switches under load conditions, push buttons used in motor control circuits, lighting switches, etc. Click each marker to see the ratings listed on this fuse. This is the reason the interrupting rating is so important. The fuse installed here was not rated for this application, causing severe damage. Time for a scenario. Please read the scenario and follow the instructions to submit your answers. A series-rated combination is described in Rule 14-014. It permits the use of a circuit breaker with an interrupting rating that is lower than the available fault current, but under strict conditions. First, the breaker must be a recognized component of a series-rated combination. In this type of system, the breaker is combined with a properly rated upstream overcurrent device. This upstream device must open before the downstream breaker, when the fault current exceeds the interrupting rating of the downstream breaker. This will prevent damage to the downstream breaker from excessive fault current. Additionally, it requires that the overcurrent devices be marked to ensure that any replacement components are of the same type and rating. Series-rated systems are often found in residential panel boards to minimize costs. Low-cost branch breakers with low interrupting ratings are protected by a fast-responding, high-quality main breaker. Though this results in cost savings, it must be understood that under a heavy fault current, the main breaker will trip. This will cause all circuits originating from that panel board to be without power. Rotating motors can contribute to the current flowing into a fault in an electrical system. The previous code did not contain a limit on motor loads for series-rated combination circuit breakers. While it was referenced in an Appendix B note, it was not enforceable. The limit now appears as Rule 14-014 Subrule F and aligns with NEC Article 240.86c. The following about protective devices will be reviewed. General requirements including sizing of tap conductors and ground fault protection. Then fuses and circuit breakers will be discussed. According to 14-100, overcurrent protection is required for every ungrounded conductor, at the point where the conductor receives its supply and at every point where there is a reduction in size. However, it is possible to have a reduction in conductor size without additional overcurrent protection, while maintaining an appropriate safety level. This is covered in 14-100 item B through G, and is often referred to as the tap conductor rules. There are different requirements for tap conductors depending on the application. Tap conductors for specific applications are addressed in the applicable sections, such as Section 26 for capacitors and cooking appliances, Section 28 for motors, Section 62 for electric heating, etc. The following are the rules related to tap conductors in general. For a tap conductor that is 3 meters or less, the ampacity must not be less than the load supplied by the smaller conductor, and not less than the ampere rating of the switchboard, panel board, or control device supplied by the smaller conductor. When the tap conductor exceeds 3 meters but is not more than 7.5 meters, a comparison is made. The tap conductor must have an ampacity that is equal to at least 1/3 the ampacity of the larger conductor, or the ampere rating of the equipment the tap conductor supplies, whichever is larger. When the tap conductor exceeds 7.5 meters, the ampacity of the tap conductor must be equal to or greater than that of the larger conductor. See a review of these rules in Figure 14-5, Typical Taps off a Splitter. If a tap conductor is over 7.5 meters, then the tap conductor amps is equal to the feeder conductor amps. Note, no reduction in tap conductor or feeder conductor amps is allowed. If the tap conductor is 3 meters or less, enclosed in metal and a single continuous duty service motor, then the tap conductor amps are equal to FLA, or full load amps, times 1.25. If a tap conductor is 3 meters or less, enclosed in metal and has more than one continuous duty service motor, then the tap conductor amps is equal to the largest motor's FLA times 1.25 plus the remaining motor's FLAs. Lastly, if the tap conductor's length is 7.5 meters or less and not enclosed in metal, the tap conductor amps is equal to the feeder conductor amps divided by 3. Here is a short activity to apply what you just learned. Enter your response and select Submit. The following is the correct answer. Click Next when you are done with your review. Moving on to the requirements for ground fault protection. This protection is required for solidly grounded systems that are 1000 amperes or more and are operating at more than 150 volts to ground, but less than 750 volts phase to phase. Typical systems that fall in this category would be 600/347 volt and 480/277 volt systems that are operating at 1000 amperes or more. It is also required for solidly grounded systems that are 2000 amperes or more and are operating at 150 volts or less to ground. Typical systems that fall in this category would be 240/120 volt and 208/120 volt systems that are operating at 2000 amperes or more. Ground fault relays used in these systems are required to have the pickup point set to 1200 amperes or less and operate within 1 second for currents 3000 amperes or more. Why is ground fault protection so important to have? Ground fault protection minimizes and, as much as possible, eliminates equipment damage and fire hazards that can result from arcing ground faults. Ground faults can cause severe damage to electrical equipment and the surrounding area due to the high levels of heat involved. In systems rated at 1000 amperes or more, a fault to ground where the impedance is significantly high could result in a fault current that will not be large enough to cause a response from the overcurrent device. As a result, these faults could go undetected for extended periods of time. Ground fault protection systems respond to these low-level faults when the overcurrent device will not. Risk can be further minimized by utilizing an ungrounded system. In this type of system, a fault to ground on one of the phases does not result in an arcing fault. A fault to ground on another phase results in a phase-to-phase fault, which will cause a large amount of current to flow, and a response from the overcurrent device. The risk is minimized by using an underground or solidly grounded system. There are two main methods to detect ground faults. The first is zero-sequence type current transformer sensor. This is described in Figure 14-9 in the code. This type surrounds all phase and neutral conductors. The current under normal circumstances is zero. When a ground fault occurs, the current goes around the sensor, and the current that goes through the sensor is no longer zero, causing the overcurrent device to trip a failure signal. The second type is ground strap sensing, described in Figure 14-10. The current transformer is installed between neutral and its ground connection to the switchboard. This will sense any current coming back through the neutral. Here is a short activity to apply what you just learned. Enter your response and select Submit. An overcurrent device's rating cannot exceed the allowable ampacity of the conductor it is protecting. However, there is an exception to this requirement. If a fuse or circuit breaker that has the same ampacity of the conductor is not available, and the maximum calculated or known load is in accordance with the rules of Section 8, the use of Table 13 is permitted. For example, using Table 2, a 6-gauge 75 degrees Celsius conductor has an ampacity of 65 amperes. Using Table 13, a 70 ampere overcurrent device would be acceptable if a 65 ampere overcurrent device is not available. Table 13 is limited to circuits that are 800 amperes or less. For circuits that exceed 800 amperes, the conductor ampacity must be equal to or greater than the rating or setting of the overcurrent device. There are several different types of fuses used for various purposes. In this section, the following types will now be reviewed: time delay and low melting point fuses, plug fuses, and the use of fuses. Low melting point fuses automatically open the circuit under predetermined overload or short circuit conditions. They are also designed to eliminate hazards from overheating due to loose connections and deterioration in the fusible element. These fuses are also available in a time delay type, which are designed to handle short-duration surges such as the inrush current of a starting motor. Since they are physically interchangeable, low melting point fuses are marked with the letter P, and low melting point time delay fuses are marked with a D to ensure that the proper fuse is used for the application. Plug fuses are screwed into a base in the fuse holder and complete the circuit. They are designed to protect the wiring. If too much current flows through them, there is a metal strip that melts or burns away, which opens the circuit and stops the flow of the current. Because of their 125-volt rating, these fuses are limited to circuits where the voltage does not exceed 125 volts between conductors, or to circuits that are fed from a system with a grounded neutral where the voltage does not exceed 150 volts to ground. They are also limited to a 30 amp maximum. Plug fuses must be non-interchangeable, which prevents them from being replaced by one with a higher rating, either by accident or deliberately because of repeated blown fuses. Type C fuses are the most common in Canada. These fuses have a cylindrical extension at the end of the fuse that becomes wider with larger ampere ratings. This prevents a larger fuse from bottoming out in a fuse holder intended for a smaller fuse. Older fuse holders can be made to comply with this requirement by using a rejection washer. See Figure 14-11. Also, plug fuses must use covered type fuse holders that have no live parts exposed while the fuse is in the holder. This allows for plug fuses to be changed by those without electrical training. Here is a short activity to apply what you just learned. Enter your response and select Submit. Here is a short activity. Enter your response and select Submit. Fuses are designed to blow when excessive current flows through them for an extended period of time. They operate on an inverse time characteristic, which means that the more excessive the current, the faster the fuse will blow. For example, this allows for a motor to start up, where the inrush current will only last for a short period of time. However, if there is a problem with the motor and the current is too high, the fuse will blow instantly. These fuses will blow within their set time frame when they are carrying 135% of their current rating, while Class C and HRCII-MISC will blow when reaching 160% of their rating. Circuit breakers, like fuses, open the circuit automatically during a short circuit or overload, the difference being that they are an electromechanical device that can be reset after an overcurrent event. They can also be operated manually. Circuit breakers must be the trip-free type, which means that they cannot be held closed during a fault. The internal mechanism will continue to protect even if the handle is held in the on position. The breaker must also have a status indicator that clearly indicates whether it is in the open, off, or closed, on position. The code also requires that circuit breakers open all ungrounded conductors, whether during manual operation or during an overcurrent action. There are two exceptions. The first is where single-pole breakers are used, as permitted by 14-010B. This rule permits a multi-wire branch circuit feeding lighting and receptacle loads to be protected by single-pole overcurrent devices, even though they share a common neutral conductor. The second exception is for three-wire grounded neutral systems, where two single-pole breakers are used in place of a two-pole breaker. This is permitted as long as the handles are tied together with a manufacturer-provided tie device, ensuring that both breakers operate at the same time. Most breakers have a fixed calibration that is factory sealed. However, larger circuit breakers may have adjustable settings. As a result, circuit breakers must be designed in a way that making adjustments to the settings is difficult. It may require a specific tool or breaking a seal. Table 25 provides the requirements for the number and location of tripping elements based on the type of system being used. To replace blown fuses safely, it is usually necessary to de-energize the circuit supplying them. Rule 14-402 requires that a disconnecting means be integral with or adjacent to the fuse holders, so that the power supply to the fuses can be interrupted easily, unless the fuses are located in a switchboard and are used to protect instruments or control circuits at 250 volts or less, on the primary circuits of voltage transformers rated 750 volts or less on switchboards, or plug fuses where the circuit has only one ungrounded conductor. Switchboards can contain fuses protecting instruments, control circuits, or voltage transformers. Because these fuses are enclosed within the switchboard and accessible only to authorized personnel, disconnecting means ahead of the fuses are frequently omitted. Plug fuses and their fuse holders are designed so that the fuse may be safely replaced while the circuit is live. In order to prevent any shock hazard to people servicing, replacing, or maintaining overcurrent or overload devices, control devices should be placed ahead of the overcurrent and overload devices. This allows the work to be performed safely, as the circuit will be de-energized when the control device is in the open position. In order to operate controls properly and safely, the control device should be readily accessible without having to overcome obstacles. Isolating switches are exempt from this requirement, as they are used for isolation and not control. If a device is remotely controlled, the controlling means must be readily accessible. All manually operated control devices must have markings that indicate if the operating handle is in the on or off position. The current carrying components of the control device must be contained in an enclosure of metal or other fire-resistant material. This is to prevent accidental contact with live parts. Control devices must be grouped together when practicable. This is often accomplished through the use of a switchboard, panel board, motor control center, or enclosed switch. This allows for quick and easy de-energization for maintenance or during an emergency. When electrical equipment is connected to more than one source of voltage, as may be the case in a system that employs both utility and renewable energy supplies, or utility and generator supplies, a potential shock hazard is created. The code gives options regarding how to safely isolate these systems from each other and the loads they serve. One option is to have a single disconnect that safely disconnects all the ungrounded conductors supplying the equipment. Another option is to have separate disconnects for each system. If this option is used, it is necessary that the disconnects are grouped together at a single location, and that warning notices are placed at each disconnect to indicate that the load has more than one source of supply, as shown in the picture. This will let operators know that all disconnects must be open to ensure complete disconnection. For control circuits operating 150 volts to ground or less that originate beyond the equipment, a separate disconnect is not required if barriers are used. Warning signs must indicate that the barriers are separating multiple sources. A control device with an off position that does not disconnect all ungrounded conductors can be an electrical shock hazard to personnel maintaining or servicing equipment. All control devices that function only as a switch and have a marked off position must disconnect all ungrounded conductors to the load they control, except where permitted by other rules in the code. The following types of switches will be reviewed: knife switches, general use AC-DC switches, general use AC switches, and general use 347 volt AC switches. To ensure the safety of the operator, knife switches must be constructed in a way that allows them to be switched off without exposing live parts, unless access is restricted to authorized personnel. Single-throw switches must be mounted with their base in the vertical plane, and in a way that will not allow gravity to unintentionally close the switch. Double-throw switches can be mounted horizontally or vertically. However, if mounted vertically, they require a positive locking device to keep the switch open when it is in the open position. Lastly, due to their construction, arcing can occur when operating a knife blade switch under load. To limit the hazard, knife blade switches rated above 600 amperes at 750 volts or less must not be used under load and are limited to isolation switching. AC-DC general use switches are designed to switch both alternating current and direct current loads. The ampere rating of the switch used is determined by the type of load being switched. For non-inductive loads, the ampere rating of the switch cannot be less than the rating of the load. For tungsten filament loads, the switch must be T rated. Tungsten filament loads are those created by incandescent lamps. A cold filament has very low resistance, which can create significant inrush current. T-rated switches have been tested to withstand this type of load. Inductive loads require the switch to be derated. Any switching of an inductive load requires the switch to have an ampere rating that is twice the ampere rating of the load. Here is a short activity to apply what you just AC/DC what you just learned. Enter your response and select Submit. Manually operated general use AC switches are designed to be installed in flush device and surface type boxes. When installed in branch circuits, they must meet certain requirements. The switch must have an ampere rating not less than the ampere rating of the load for tungsten filament loads at 120 volts maximum, non-inductive loads, and inductive loads operating with no less than a 75% lagging power factor. When installed in 120 volts or 277 volt circuits, they must have a minimum 15 ampere rating and inductive loads. 347 volt AC switches are used to control non-inductive loads, tungsten filament lamp loads, and inductive loads that operate at not less than a 75% lagging power factor. They must also have a minimum 15 ampere rating when used on a 347 volt circuit. To limit the likelihood that a switch with an incorrect voltage rating is used on a 347 volt circuit, special device boxes are used. These boxes use mounting screws that are further apart, which prevents the installation of a switch with other than a 347 volt rating. A remote control circuit allows electrical equipment to be turned on or off at a remote location. The power supply can come from the same source that supplies the electrical equipment. When the control circuit extends beyond the electrical equipment enclosure, 14-608 requires a disconnecting means for the control circuit at the controller. This disconnect is not necessary if the equipment disconnect also disconnects the control circuit supply. This can be accomplished by connecting to the load side of the equipment disconnect. They must have a way to be disconnected, unless the controller also disconnects the control circuit. Receptacle configurations are standardized according to voltage and ampere ratings as shown in diagrams 1 and 2. Configurations for locking and non-locking types are arranged to prevent the connection of a load greater than the rating of the receptacle. Branch circuit overcurrent protective device supply receptacles are rated less than or equal to the rating of the receptacles. Outlets or luminaires are often controlled from more than one location. For example, a luminaire in a stairwell that can be controlled from either floor level using three-way switches. Rule 14-604 requires that switches used to control outlets or luminaires from more than one point be connected so that all switching is done in the ungrounded circuit conductors only. This ensures that the outlet or luminaire does not contain an energized conductor when the switch is off, and that the identified conductor maintains its reference to ground. Like all other electrical equipment, panel boards have a current rating based on the internal components, such as bus size, lug size, etc. As a result, 14-606 states that the rating of the overcurrent device protecting the panel board cannot exceed the rating of the panel board. The minimum rating of overcurrent device would be determined in accordance with the requirements of Section 8. In the case of a panel board that supplies motors, the panel board overcurrent protection may be oversized provided that 90% of the loads supplied by that panel are motor loads. This is to accommodate for the starting surge of the motors. There are several options for the location of the panel board overcurrent protective device. It can be part of the panel board, better known as a combination panel, as shown in the picture. It can also be in a separate enclosure ahead of the panel board, or it may be in the primary of a transformer supplying it. When the latter is the case, the panel board must have a rating greater than or equal to the primary overcurrent device rating, multiplied by the ratio of primary to secondary voltage. Solid-state devices are never to be used as isolating switches or as disconnecting means. One of the reasons for this is that solid-state devices are controlled by software, which can be overridden by unqualified people. This can cause the contact to re-energize the equipment when it is required to be locked off. See CSA Standard Z460 and Rule 2-306, Sub-Rule 3. A supplementary method of disconnection must be used when a solid-state device is failing or leaking. This failure or leaking can cause the transfer of energy between two or more sources. This supplemental method of disconnection must be connected into the circuit in a way that will prevent the transfer of energy between the two power sources. It must be an integral part of the solid-state device and installed as close as possible to the solid-state device. To ensure the safety of personnel operating or working on systems with solid-state devices, 14-704 requires that the supplementary disconnecting means has a warning sign to indicate that the disconnecting means should be opened if power fails in any power source or before servicing any part of the circuits of the other power sources. The sign must also state that both the line and load terminals may be live, even when the disconnecting means is in the open position. Item B requires that all other disconnecting means in the system have signs warning that other power sources exist in the system, and that the supplementary disconnecting means must be open to prevent feedback from those systems. Here is a short activity to apply what you just learned. Enter your response and select Submit.
You covered a lot in this course. This summary helps you to recall the main concepts and requirements of this code section. You have now completed the learning on the main concepts and requirements of this code section. Next, you will take the open book quiz through